Hello, everybody. Welcome back to our CSAC weekly research seminar. It's a real pleasure to welcome this week Dr. Lindsay Krall, who will be talking about nuclear waste, a critical analysis of small modular reactors. Dr. Krall is a postdoctoral fellow at CSAC this year, funded by the MacArthur Foundation. She has a PhD in geochemistry from the University of Stockholm and has been working on issues related to geological repository development and the back end of the nuclear fuel cycle for quite a few years, and she's here to talk to us about some of our research. Dr. Krall, why don't you take it away?
Hey, hello. Thanks for the introduction, Harold. Today, June 4th, 2020, I will characterize the implications that small modular reactors will have for the generation and management of commercial nuclear waste. Since the mid-2000s, small modular reactors, or reactors with electric capacities less than 1/3 that of a standard commercial reactor, have been heralded as the future of nuclear energy in the US because they are said capable of overcoming each of the challenges facing nuclear energy today. Although SMRs have not formally entered the market, some designs are well along in the staging process. For instance, NuScale LLC may soon obtain an NRC license for an IPWR that, like existing reactors, would use water as a coolant and moderator. However, the majority of SMR proposals registered with the IAEA qualify as advanced SMRs, employing liquid metal, molten salt, or gas coolants. Conversely, many advanced reactor designs classify as SMRs, so the concepts of advanced nuclear and small modular reactors are intricately related. Vendors are focusing RD&D efforts on methods to accelerate reactor construction and pushing to relax siting requirements for SMRs. But at the back end of the fuel cycle, few high-quality radiochemical descriptions of SMR waste streams have been published. Nevertheless, many vendors assert that these reactors will reduce the burden of commercial nuclear waste disposal. However, the metrics employed to justify these claims, namely in terms of high-level waste, mass, and radiotoxicity, do not convey the radiochemical information needed to assess the technical basis for SMR waste management and disposal. Also rarely discussed are the low and intermediate level waste streams that will contain long-lived radionuclides and so will warrant disposal in a geologic repository. Here, I analyze 3 distinct SMR designs in terms relevant to the planning of nuclear waste storage and disposal. Each of these designs are widely marketed, and enough design data has been made available to support a semi-quantitative waste analysis. So nuclear energy is generated from the heat released by the fission of a heavy uranium or plutonium nucleus. In addition to heat, this reaction produces radioactive fission products and 2 to 3 neutrons. The fission products consist of short and long-lived radionuclides with complex physiochemical properties that create short and long-term challenges for nuclear waste disposal. The neutrons are a more productive force, with the potential to promote fission of other heavy nuclei in the fuel lattice. However, a fraction of these neutrons will leak out of the core through its periphery. This leakage probability is correlated to the surface area to volume ratio of fuel, which is larger in the core of an SMR. Enhanced neutron leakage is well understood to reduce fuel burnup in SMRs. Burnup, a measure of fuel efficiency, is inversely proportional to the mass of spent fuel generated per unit energy extracted. Burnup factors significantly into the composition of the spent fuel waste product. SMR efficiency losses incentivize the use of fuel with an initial fissile composition greater than 5 weight% uranium-235, of a radial neutron reflector to surround the core, and of a neutron moderator other than water, for instance, graphite. One or all of these design changes are incorporated into each of the SMR designs registered with the IAEA. But even with these modifications, fuel burnup in SMRs will still be lower than in a large reactor of a similar type and fuel cycle. The plutonium in low burnup SMR fuel will be relatively pure in plutonium-239, which Alexander Glasser at Princeton University has studied in the context of weapons proliferation. Here, I will analyze SMR spent fuel composition in terms of recriticality, decay heat generation, and radiochemistry. Furthermore, near-core components, such as the newly integrated neutron reflectors, will absorb leaked neutrons and thereby become activated. Moderator and coolant materials inside the core will also gain this induced radioactivity despite their low power output. Neutron fluxes within and around SMR cores are similar to a large reactor. For instance, the power capacity of the NuScale IPWR will be less than 20 times that of a large pressurized water reactor, but the neutron flux at its core periphery will only be about 30% lower than the large reactor. Due to disproportionately high neutron fluxes in SMRs, they will generate disproportionately large low and intermediate level waste streams. So SMRs using semi-traditional pressurized water reactor technologies are often designed as integral PWRs or IPWRs because their steam generators and control mechanisms are housed within the pressure vessel in order to facilitate the rapid on-site assembly of the reactor. So here you can see this inner reactor vessel where you see this steam riser tube. This is all going to be in contact with the primary coolant that flows through the core, where it can gain radionuclides that have been released from ruptured fuel pellets. And these radionuclides can contaminate all of the surfaces that come in contact with the primary coolant. So this is one waste stream for what is generally considered contaminated low and intermediate level waste, which is mostly short-lived, whereas the activated low and intermediate level waste is generally more long-lived, so it would require disposal in a geologic repository. So here I've shown the designs of a standard full-scale PWR on the left and a small IPWR on the right. And from these designs, I've made calculations for the volumes of activated and contaminated waste streams. And the burnups I calculated from the NuScale license application. And the results were consistent with 2 previous studies of IPWR fuel burnups. So although long-lived low and intermediate level waste is by volume a relatively small waste stream, the activation of steel generates a mixture of short and long-lived radionuclides that pose exposure risks that must be mitigated over short and long timescales. Short-lived radionuclides in the activated reactor components, such as cobalt-60, will emit gamma radiation. So plans to decommission shutdown reactors must seek to minimize worker exposures to radiation. In the US, this may involve on-site storage of activated reactor components for up to 60 years to allow for the decay of short-lived gamma emitters. Once the reactor components are finally moved off-site, activated reactor materials should be disposed of in a geologic repository that will limit and delay releases of long-lived radioisotopes of nickel, niobium, and molybdenum to the environment. Although IPWRs will experience a diminished fuel burnup that leads to their discharging a relatively large volume of high-level waste or spent fuel, the chemical form of this will be similar to that discharged by existing reactors. This material, nominally uranium dioxide, shows good stability under ambient environmental conditions. Given the high radioactivity and heat generated within the matrix, this chemical stability is welcome at storage and disposal facilities. However, the fissile isotope composition of low burnup spent uranium dioxide discharged by Pwrs will be different from that of the large reactor, and the associated consequences for this will be discussed later in this presentation. So in the popular media, molten salt reactors have been referred to as thorium reactors. More correctly, thorium is a potential fuel that could be used in a molten salt reactor. However, most of the proposed molten salt reactor designs would initially be fueled by uranium, which might serve to breed fissile isotopes in a thorium blanket. My analysis focused on thermal spectrum molten salt reactor designs. Although fast spectrum molten salt reactors have also been proposed, they're typically designed as large reactors and so are not covered here. Conversely, most of the thermal spectrum molten salt reactors classify as small reactors. These designs employ graphite as a moderator and reflector. The graphite is in the form of a block that constitutes up to 90% of the in-core volume of a molten salt reactor. The graphite has tubes drilled into it through which molten lithium or sodium fluoride containing dissolved fuel isotopes flow. Unlike existing light water reactor fuel, which is contained within zirconium cladding, the fuel for these reactors will be a mixture of radioisotopes and molten salt. This fuel salt will duly serve to cool the reactor. The graphite in the core will not only be large in volume, its lifetime will be limited by radiation damage to 4 to 12 years for the more common molten salt reactor designs. The lifetime of the steel reactor vessel will also be limited because it will corrode rapidly when in contact with the molten fuel coolant salt. On top of the anticipated large and low and intermediate level waste streams associated with these designs, molten salt reactors entail fuel burnups even lower than an IPWR. Terrestrial Energy states that their integral molten salt reactor design, shown here on the right, will have a fuel burnup of only 26 megawatt days per kilogram. So in the sodium-cooled fast reactor category, designs as small as 2 megawatt thermal have been proposed. Although these fast reactors do not require a neutron moderator like graphite, they will require neutron reflectors and radial shielding, generally consisting of steel and tetraboron carbide respectively, shown here in orange and red for the horizontal and vertical cross sections obtained from the Pwrs design. Reflectors and shielding will generate decommissioning waste that require radiochemically informed management. The liquid sodium employed to cool the reactor is also destined to become radioactive waste. It will contain radionuclides gained through contamination and neutron activation pathways. However, plans to manage and dispose of this material must consider its high chemical reactivity. Metallic sodium is what we call pyrophoric. That means it burns when exposed to water. Hence, it should be chemically treated before it can be disposed of in a geologic repository where water will inevitably be present. Treatment of the sodium coolant from shutdown experimental fast reactors operated during the late 20th century presented a significant decommissioning challenge and was largely accomplished through a pilot-scale water-based process. This process needs to be performed under an oxygen-free atmosphere to avoid explosion of a hydrogen byproduct. The low and intermediate level waste issues for sodium-cooled SMRs will be compounded by the high initial fuel enrichments and low fuel burnups. The Pwrs reactor shown here, having an output of only 30 megawatts thermal, will achieve a burnup of only 34 megawatt days per kilogram using fuel enriched to 18% uranium-235. Hence, like the small IPWR molten salt reactors, sodium-cooled fast SMRs will achieve lower fuel burnups than existing light water reactors. So having described the pathways for radioactive waste generation and the qualitative properties of these wastes, I here show the volume of the various waste streams by waste and reactor type. As you can see, not only are the energy equivalent volumes of low and intermediate level decommissioning wastes increased dramatically in the SMRs, but their spent fuel volumes, shown in green, will also exceed that of a traditional PWR. Predisposal processes to treat the chemically reactive sodium and corrosive salt fuels and coolants are anticipated to generate additional low-level wastes, which have not been included in this analysis. In addition, I do not show any uncertainty bars, but the full-scale PWR waste streams, having been analyzed in detail for existing reactors, should be viewed as more certain than the SMR waste streams, which in themselves I have strived to express in terms of a lower bound. Well, far beyond volume, a spent fuel management and disposal system must take into account the heat generated within the material through radioactive decay, the criticality risks associated with its fissile isotopes, and the chemical form of the radionuclides within the material. Initially, the decay heat is dominated by contributions from the fission products, shown here in red, and is managed through a decades-long period of interim storage at Earth's surface, either in actively cooled ponds of water or in passively cooled concrete casks. After a few decades, the material can be loaded into corrosion-resistant disposal canisters in a way that mitigates the recriticality or a fission reaction sustained by the fissile remnants in the fuel. After cooling, the spent fuel should be placed in a geologically stable rock formation at a depth where groundwater flows slowly and has a composition that promotes the chemical stability of the uranium dioxide fuel. This aims to allow for significant radioactive decay before a canister is breached. Note that after 10,000 years, the spent fuel activity will have decayed to 1/1000th that of that present a few years post-discharge. Although actinides such as plutonium are responsible for much of the long-lived radioactivity, this class of radionuclides is relatively immobile in oxygen-free water if incorporated into a uranium dioxide fuel matrix. Nevertheless, the molten salt and metallic fuels that many SMR developers intend to use are highly soluble, and so will need to be chemically processed into a durable waste form before they can be safely disposed of in an underground rock formation. Fuel conditioning will increase pathways for occupational radiation exposures as well as for weapons proliferations. In fact, the technologies that the U.S. Department of Energy is developing to treat molten salt and sodium bonded fuels can be easily modified to separate plutonium and so represents a weapons proliferation risks. Ultimately, the low burnup fuels that SMRs will discharge will not significantly reduce the duration of interim storage, the size of a geologic repository, nor the associated long-term environmental doses, because these are heavily influenced by short and long-lived fission products. Thus, SMRs will offer no significant benefit to heat management of and environmental doses from spent fuel. Rather, low burnup SMR fuels contain additional proliferation and recriticality risks due to the relatively high concentrations of fissile plutonium-239 and uranium-235 isotopes in these fuels. The possibility that a spent fuel canister fails and is flooded by groundwater cannot be excluded from the safety case for a geologic repository. Since water is an effective neutron moderator, this could promote a sustained critical reaction that thermochemically degrades the repository system. Hence, repository safety assessment involves criticality calculations, which determine whether the concentration and amount of fissile material in a spent fuel canister could sustain a critical fission reaction. According to criticality analysis for various repository designs, PWR fuel that initially contains 5% LEU should be irradiated to a burnup exceeding 39 megawatt days per kilogram in order to diminish the likelihood of recriticality. In this case, the concentration of fissile uranium-235 and plutonium-239 in the fuel will be around 2 weight percent. The figure on the right roughly illustrates the relation between critical mass and fissile isotope concentration for a spent fuel assembly. The area to the bottom left of the black criticality curve shows the subcritical region, and the top right shows the supercritical region. So a fuel assembly discharged by a full-scale PWR initially enriched to 5 weight percent LEU with a burnup of 50 megawatt days per kilogram, which is standard for existing reactors, will contain less than 2 weight percent uranium-235 and so a large mass of material would be required to sustain a critical reaction in a water-flooded canister. However, with decreasing fuel burnup and a concomitant increase in fissile isotope concentration here on the horizontal axis, the critical mass decreases. Since this decrease is exponential, note here the logarithmic scale for the y-axis, the canister fuel capacity should exponentially decrease with increasing spent fuel fissile concentration. Likely, the SMR trend towards higher initial fissile concentrations and lower fuel burnup will have severe consequences for designing an economic spent fuel canister. Furthermore, if individual fuel assemblies will contain a supercritical mass of fissile material, such as may be the case for sodium-cooled fast reactors, shown here by the yellow triangles, then an irradiated assembly may need to be disassembled in order to load a smaller number of fuel rods into a canister. These operations would introduce radiation exposure pathways before the fuel is placed in a repository, a time during which the spent fuel radioactivity is high. So I've shown that SMRs will produce more spent fuel and low and intermediate level waste than existing light water reactors. And much of this waste will present significant disposal challenges with respect to the chemistry of the fuel, coolant, and moderator materials, and with respect to the fissile isotope compositions. Although I've only assessed 3 out of the dozens of proposed designs in detail, many of the SMR waste challenges can be traced back to the issue of enhanced neutron leakage from the small core. This is driving the lower fuel burnups and the associated increase in spent fuel fissile isotope concentration, as well as the increase in decommissioning waste. Thus, the conclusions drawn here are broadly relevant to many SMR designs. As a consequence of the waste management challenges that spent SMR fuels will propose, it would not be a surprise to see increased industry advocacy in the realm of spent fuel reprocessing. an activity that is widely recognized to pose a risk for nuclear weapons proliferation. In fact, developers who tout remarkable reductions in high-level waste often assume that a particular SMR will be implemented together with commercial spent fuel reprocessing. And fuel designs for many molten salt and sodium-cooled reactors are chemically optimized to facilitate their industrial reprocessing. An obvious follow-up to this study would be to further probe the implications that SMRs, the implications that the back end of SMR fuel cycles will have for nuclear weapons proliferation. And with that, I would like to thank MacArthur Foundation and CSAC, and I'm happy to take any questions.
Great, Dr. Krall. So now we have an opportunity for some Q&A. Please remember to enter your questions in the Q&A box in Zoom, and I'll go ahead and read the questions as they come in. The first question is from Rod Ewing, and he asks, what would be the typical service lifetimes of different types of SMRs?
Well, it depends on the SMR. A semi-traditional integral pressurized water reactor would have a lifetime of 60 years, which is similar to that of large reactors. Where molten salt reactors seem to have the biggest issue with the lifetime of the reactor vessels themselves. Their lifetimes are around 8 years. For the various proposed designs, but it's not, so this reactor vessel lifetime is influenced by corrosion and also the issue of graphite damage. So yeah, when you have such a short lifetime, then you're going to increase the rate at which you're generating, decommissioning waste. So even in some molten salt reactor designs, I've seen it proposed that the fuel salt is drained into a new reactor vessel, so that instead of discharging the spent fuel, you're discharging reactor vessels and graphite, whereas that spent fuel can continue to be irradiated if you have, this reprocessing system built into the reactor, the power plant. So yeah, many of these concepts greatly diverge from how we think about, nuclear waste traditionally. Sodium cooled fast reactors, the Pwrs design that I showed here had a 30-year lifetime, and that seems to be similar for other sodium cooled fast reactors.
Thank you. Stephen Sondheim asks where you stand on the mass deployment of SMRs. Do you view them as economic as compared to other sources such as renewables? And how long would it take to implement or install a significant base that would have a meaningful impact on climate change? So several questions.
Okay. So I guess the first question would be, are SMRs economic to construct? The whole motivation behind building these reactors is a claim that they would be economic. So the claim that small reactors would be more economic than a large reactor greatly diverges from how we think about energy economics today. We have this idea or a theory or a law of economies of scale. However, small modular reactor developers are promoting the idea of economy of multiples, where you can mass manufacture these reactor modules and just ship them out and plug and play. At the reactor site, you're going to plug and play the reactor. There's not going to be a lot of construction workers putting together this big machine. The caveat there is that to make SMRs economic, you need to deploy hundreds or thousands. I don't know. Nobody knows how many SMRs would need to be deployed to make them economic. And honestly, in some of the cost estimates I've seen, the cost of SMRs, namely IPWRs, those have increased a lot actually since the mid-2000s, when the idea of SMRs first gained so much traction. So like more recent cost analysis put them at a cost more comparable to traditional nuclear. So I am very skeptical that SMRs will be more economic on the front end. That may be the case. They're promoting these relaxed regulations that could make SMRs more economic. But on the back end of the fuel cycle, I have no doubt that the costs are going to be increased, and those costs will be forced on to future generations. So where do I stand on using nuclear to combat climate change? I personally think that nuclear is valuable, at least for the rest of this century. Beyond this century, I think renewables are a much better option, but just sort of the grid scale energy storage, the distribution, all of these things are not together yet. So we really just need to use what's available to us. And there has been a lot of progress made in spent fuel disposal, but that is mainly with respect to disposing of the spent fuel from traditional light water reactors.
Thanks. We have a question from Lori Johnston about whether SMRs are being developed for applications in space related to fuel, water, energy, supporting human habitation in space.
Yeah, when the cost estimates for SMRs increased, then advocates started promoting niche applications. So one of those niche applications is in space exploration. But with respect to whether space exploration will be valuable in getting water and other resources for human habitation, I'm not really sure. I don't see where SMRs how they would generate water in space for human consumption.
Thanks. We have a question from Deepak Das. Could you tell us a bit more about where and how these reactors are being built and what kind of societal impact this has had? Are there disproportionate societal effects from building these type of reactors compared to others?
Thus far, these reactors have mainly been used in military applications, such as, army bases in Greenland and in Alaska. But that was mostly very early, 1960s, 1970s. Today, there aren't any SMRs being built. It's a very common misconception that these are like actual existing reactors, whereas mainly they just exist on paper and in the minds of their developers. The societal impact, what concerns me a lot is that SMR developers are advocating to relax the siting requirements. Okay, so one of the regulations they want changed in the US is to reduce the emergency planning zone. You know, this radius around a commercial reactor, which is a 50-mile radius. So within that 50-mile radius around your reactor, anyone trying to build the reactor is going to have to engage local communities and inform them of evacuation plans if there's a nuclear disaster. So, you know, that's a lot of, you know, community engagement you have to pay for. So, you know, one area where SMRs could be made more economic is in making that radius smaller. And that would make it easier to site SMRs near population centers. So I don't know, hollowed out industrial center having an SMR, perhaps, you know, but then I do not think it would be prudent to have SMRs that have, you know, potentially, you know, like very flammable fuels stored close to population centers, like, you know, suburbs and cities. So that, I think, will be a major question for society when it comes to SMRs.
Great. The next question from Richard Denton was actually addressing the military versus civilian uses of SMRs, which I think you just addressed, although Richard, feel free to add the question back at the Q&A if you want to be, at the end of the Q&A if you want to be more specific. From Dr. Francois Diaz-Morin at Amphos 21 in Spain. Thanks for a very interesting talk. He says his question is about the management of waste from IPWRs and MSRs. Would there higher criticality risks require extending the period of surface storage before they can be disposed of in geologic repositories?
I don't see why the criticality risk would diminish with time. So the point of interim storage would be that, like, you have the decay of the heat. So once you emplace the fuel in the repository, the heat generation is lower. And that heat in the initial stage is mostly driven by fission products, whereas criticality is mostly driven by fissile isotopes. So if you store spent fuel on the surface for longer, like your uranium and plutonium aren't going to decay that much unless you have the fuel stored on the surface for thousands and thousands of years, right? Because the half-lives of uranium-235 and plutonium-239 are, you know, tens of thousands of years. So a longer period of surface storage won't reduce the recriticality risk. I think that would, you know, surface storage would be even worse because those criticality risks could also occur while the fuel is in interim storage.
So from Kylie Keys Holland, sorry if I'm mispronouncing your name, what would be the additional costs associated with waste disposal from SMRs? And how much impact would there be from the dispersed nature of SMRs versus traditional large nuclear reactors? So how much impact would that have on the issues of costs associated with waste disposal, having many SMRs versus a small number of traditional power plants?
Well, transportation of nuclear waste to interim storage facilities and to final storage facilities is not an insignificant cost on the back end. So I would think when you have a lot of dispersed SMRs, you're going to be dealing with increased transportation costs, and these could be much higher. But A lot of SMR plants are actually designed to house multiple of these reactor modules, so that a SMR power plant could be of a comparable size to that of, you know, traditional large reactors. In terms of what will the final waste cost amount to, it's a very interesting question. I really wish we had more cost data, especially in the US when it comes to nuclear waste disposal. But unfortunately, since the US has little to no experience with transporting commercial spent fuel, you know, I don't know what that costs in this country. There's just no cost data because our program for spent fuel management has been stalled for a decade. All the cost estimates that were created were done so more than 10 years ago. So it's a great question, but I think what can be said is that SMR, you know, the cost of SMR waste management will exceed that of managing waste from the existing reactors.
So the next question from Melissa Carlson actually touches on this, and maybe you've already addressed this. She says, fantastic presentation and extremely critical research. So she wanted to, maybe you could characterize a current state of debate about what is the policy debate about disposal of SMR waste? Is this something that is an issue for debate?
Oh, SMR waste, disposal of that waste is not a policy debate. Mostly vendors are saying to policymakers, these reactors are very beneficial when it comes to, you know, waste reduction. And, you know, like I said, they're not providing any data really to back up that claim. And from what I've seen, some policymakers are very just genuinely confused, and they want real information, but, you know, there's not a clear pathway for them to get that information. There is a bit more policy debate around the existing spent fuel in the US today. Like I said, our program has been stalled for 10 years. That's mostly due to, you know, political issues. Like, it's been a highly politicized topic. But when it comes to actually confronting the waste disposal issue, it, you know, just isn't that high on the priority of some policymakers. It's really just a radioactive topic to handle politically.
Nicely put. From Professor Sig Hecker, he says, I've always thought the main attraction of SMRs is economics. Do your findings greatly diminish the potential economic benefits of SMRs?
I would say on the back end, it could. You know, from what I've seen, a lot of the cost estimates for, I mean, I haven't seen that many cost estimates for SMRs, but the ones I have seen shown that they are not that cost competitive with traditional reactors. Obviously, you know, these cost estimates are just sort of a shot in the dark. They're always exceeded by several factors when it comes to actually constructing the reactor. Whether SMRs can, you know, avoid that cost escalation in the construction process, maybe, I don't know. I'm simply trying to characterize the waste, and from my findings, I can say that SMRs will increase costs on the back end. They will not decrease back-end costs, and back-end costs are not really factored into the cost of reactor construction.
Thanks. For Brett Leslie, you seem to indicate that LILW required a deep geological repository for disposal. rather than shallow land disposal. Can you clarify the disposal pathway for the waste, LILW, and spent fuel?
So I should have been more specific. You have long-lived low and intermediate level waste, and you have short-lived low and intermediate level waste. And the short-lived intermediate level waste, yeah, it can go to shallow landfill like disposal. The long-lived low and intermediate level waste, in the US, that is current regulations mandate that those be sent to a geologic repository because like the longer lived your radionuclides, the more isolated you want it to be. So when maybe the presentation wasn't as clear in those categories, but the manuscript I'm writing is clarifies that a bit better.
Great. So I have 3 questions left, which I think we still have time for. From Colin Garvey, M.W. Ramana, and one last one from Sig Hecker. So from Colin Garvey, if large-scale reactors are not acceptable to a risk-averse public, and if SMR manufacturers could convince the public to accept new designs, could the benefits of reducing reliance on petroleum-based fuels or hydrocarbon-based energy sources be worth the costs of higher radioactive waste generated by SMRs?
So I am unclear as to like large light water reactors are not acceptable to the public. I'm not extremely good with tracking, you know, political polls and views on nuclear energy, but the last I checked that was that the American public was in favor of nuclear energy. Small modular reactors, this idea that they'll be more politically or socially acceptable because they're smaller. A lot of this narrative has been constructed by developers. Will, you know, SMRs be beneficial in mitigating climate change if the public can accept them? I don't know. I mean, it's like climate change is in our faces right now, whereas these recriticality risks are something that would have to be dealt with in 30 years. But I think like there are ways that you can design SMRs to be, you know, more aware of the issues we're dealing with at the back end of the fuel cycle. So I really think that there just needs to be like a greater dialogue between the back end and the front end. But, you know, this just isn't happening, and it hasn't happened. So I don't know. I mean, if I were choosing how to move forward with a clean energy agenda, I would favor large light water reactors, and I would demand that, you know, more improvements to their safety are implemented, because there are ways that you can improve, you know, the safety of large reactors.
Thanks. From M.W. Ramana, he said, I would like to bring you back to the main focus of your talk, which is figuring out the spent fuel nuclear waste implications of these paper SMR designs. Can you tell us more about what programs you used to model these reactor designs? Did you use MCNP? Was there enough information available to do the modeling in detail, or did you have to make assumptions? And did you reach out to any of the developers, and what was their reaction?
I did. Initially I tried reaching out to the developers, but as it turns out, there are a lot of challenges in modeling small modular reactors. You know, you can't, it's not straightforward to use existing modeling software to model like such a drastically different reactor design. So, I mean, that's a big area of research in nuclear energy, is modeling advanced reactors. I simply just looked at what's been published. So the burn-ups I showed are what are showed by the SMR developers. And then, yeah, for thermal spectrum, IPWRs and molten salt reactors, like your fuel composition is going to be fairly similar for a specific burn-up. You know, whether, you know, that's been irradiated in a large reactor or a small reactor. I did use the Origin software, what's it, Origami. It's like a pre-constructed library, but it has just a very limited type of fuel. So it's mostly just for light water reactors and you know, existing reactors. It's not something that's that relevant to molten salt or sodium fast reactors.
Thank you. One more question from Sig Hecker. In your abstract, you say SMRs have received bipartisan congressional support based on the pretense of nuclear waste benefits. Has that been a major argument for SMRs made to Congress, and who's making that argument to Congress?
I would say that, yeah, there are just sort of blanket groups that advocate nuclear technologies. And so a lot of Congress people do not necessarily distinguish between advanced reactors and small modular reactors. So it's mostly when it comes to advanced reactors, you know, that's where these waste benefits are really being promoted. So it's in a lot of the advocacy groups in Washington. If you go on their websites, you'll find SMRs have great benefits with respect to radioactive waste. And so these are the same groups that are engaging with policymakers in the US, and they're also engaging with reactor developers. So, you know, to the non-expert, all these different classes of reactors are not easy to navigate. There are SMRs that I think have maybe more potential when it comes to waste management. Certain designs, I did not analyze them here because there's less data. So I mainly focused on the designs that we have experience with so far in the form of experimental reactors at national labs. But there are more advanced designs, but these have the disadvantage of having less data available to perform this type of analysis.
And so maybe the last question, and we'll wrap up then by noon, by 1 p.m., is did you say something about what the timeline is for implementation of SMRs? What is, you know, by 2040, are these envisioned to be in commercial use, or is the timeline longer than that? Because as you say, they've been on paper for quite some time now. So what does that debate look like?
The timeline was for 2016. So obviously we're beyond that. I've seen in the next decade, you know, in the next decade, we want SMRs, and like there are timelines that say these reactors will be available on a large scale by 2040. Perhaps that will be the case. I will only say that I hope with this accelerated development of these reactors, I only hope that people are thinking about the back end of the fuel cycle, you know, before a particular design is deployed, rather than after.
Okay, well, that seems an appropriate note on which to end the talk. Thank you very much for a great talk and great Q&A session. And everybody, please join me in thanking Dr. Krall for her participation in the research seminar.
Yeah.